and then he switched to mathematics, and he spent 10 or more years in Cambridge and Edinburgh. Yes, and so now he's working in Stephen Wolfram Institute, and currently his project is about general graph theory and application to different understanding of different phenomena. But this time I just give him a free topic and I said that, Carlos, you can tell about anything you want, interesting is. And yes, this last summer, last autumn, actually, Carlos came into Ukraine and stayed in Lviv, and then came to Kiev also. So he's very sympathetic to Ukraine and everything. So yeah, so that's why he was very excited with this opportunity, and I believe it's good idea to have such a lecture. So please, yeah, Carlos, I think you can spend few minutes just to say what you want, and then we can start, I think. Yeah, thank you.
Okay. Right. So, Dobry den, everyone. That's the extent of my Ukrainian as far as it goes. I hope that it will improve. But yes, it's a pleasure to be remotely joining you over there. As Olexii just mentioned, I visited Lviv back in November and spent the weekend in Kiev as well. And I can see in the map where you guys are. And I believe I was, oh yeah, that's next to the Freedom Square, right? The square with the freedom sign, right? Yes. So yes, I remember, I know where you are. So I feel like I am more insight on location than just abstractly seeing one screen on the computer. So yeah, so there's a couple of people that might join the Zoom call from my side. I shared the link with the guys. So maybe I'll say maybe a couple more words about the non-scientific stuff towards the end, and maybe there's more of a group of people gathered here. And I think Olena has just also joined, and I don't know if she's hearing me, but I should say. Oh, you are in the room.
Yeah.
Oh.
Okay. I'm here.
Oh, great. So.
He actually I think he kept in mind the other Olena, but okay.
Oh yeah. Oh yes. I guess we have a similar problem. I have also a very common name in Spain, so I get that all the time. But Olena is on the call, right? But this is Olena that I knew before today, right?
Okay.
So I was just going to say a big thank you to Elena, who made the connection here. Maybe so everyone understands where I was coming from. In fact, I'll share my screen because I'll talk over an image. I think it might be more useful. How am I going to do this? I think I'm going to do it like that. Can everyone see this?
Yes.
How do I? It's on the way. Here we go. Is that visible to everyone?
Yes, that's cool.
Yep. So this is the topic that I chose. I'll just move to the first slide to basically talk about my two affiliations. As Olexii just mentioned, my job is at the Wolfram Institute. I am a mathematical researcher over there. I've been very fortunate to be now principal investigator. We have a grant, and we are conducting several projects. There's opportunities for people in physics who might be interested. So this is something that maybe some of the physicists in the audience might be interested to check out. But in any case, I'm also the founding director of the Society for Multidisciplinary and Fundamental Research, and this is ultimately how I got in touch with Olena, and we invited her as one of our speakers last year to our summer school. But she happened to be in Kiev at the time, and so she couldn't come. And we got in touch. We had really interesting conversations, and hopefully she'll be joining us this summer in Spain, in Valencia. And that's how I eventually got to know Olexii because I mentioned to her that I was interested in collaborating somehow using my scientific network and generally interconnecting with Ukraine somehow. And Olena immediately made the link with Olexii, and I visited Lviv, and it was fantastic. And I really, really loved Kiev. I had my hosts there were a family that I knew from Spain actually, and I was amazed by many things, but the food especially was incredible. So I have to say, as a Spaniard with high standards for gastronomy, I really enjoyed Ukrainian food a lot. So I'm looking forward to going back, especially for that. So anyway, as I just said, my trajectory has been mostly in physics and mathematics. I did kind of the traditional academic path. I went to university to do a degree in physics. Then I did a master's and PhD in mathematics and mathematical physics. And then I've worked as a postdoc for about now 5 years or so in several topics surrounding dynamics, geometry, networks, algebra. That's why I put those words over there. Some general topics in those areas. I'm not going to talk too much about those. In fact, I'm not going to mention much at all. But right now, as I said, I just became principal investigator on this grant, and we have a very specific problem that we're looking into. Many of you maybe have heard of Stephen Wolfram. He has been sort of a champion of the sort of approach to complex systems and computational systems that takes this sort of automated perspective. And I joined their institute as more as a mathematician, but ever since I was able to formulate a project that has now been funded, and I will tell you about it today. But the point of this talk, as it was in the opening, can I use? Okay, yeah. The point of the talk is to make a parallel between particle colliders and computers. And I mean, I'm sure that a lot of people. Sorry, I have a floating panel here that maybe we can move. Yeah. I'm sure that a lot of people might have heard about how particle colliders, particle accelerators are very big machines, very complicated, and so maybe the comparison with computers is not so overblown. Indeed, there are many computers involved in the particle colliders and the science done around them. But here I want to make a case that I'm going to take the next 40 minutes or so of this talk to try and argue that what we might be doing nowadays in the 21st century with our computers is actually similar to what we were doing about a century ago in particle physics. And for that, I'm going to give you a brief recount of what particle physics is. I know basically half of the audience are physicists, so this will be a very basic retelling, but hopefully it will be useful to set the stage. So let's begin with that. Let's begin with a brief history of particle physics. So I have here what I consider to be two of the most intuitive and easy to grasp for any person, not even a scientist, examples of particle physics. So on the left-hand side, you have the double slit experiment, right? This is a very relatively simple setup that happens to be very surprising. So for those of you who haven't seen it, you see the diagram where you have I mean, forget about the words right now. This is electrons and beam gun and so on. Just imagine you have some kind of emitter of waves. Could be light, could be ripples on water, could be anything. And then you have sort of two openings, and then you have a screen at some distance. So it's clear that when you do this experiment with light or with waves of some kind, you get an interference pattern. And I mean, that's not surprising when you understand how waves work. Everyone expects this to be the case. However, if you imagine that you're kind of projecting little balls, like ping pong balls or some kind of projectile that is, particle-like, you wouldn't, of course, expect this sort of interference pattern. You would expect that they sort of bunch up near the openings, and then they sort of, in a kind of normal distribution, they go to the sides. But what is very, very surprising is that when you do this experiment for electrons, which in some sense people might think of electrons as very, very small balls, right? Very, very tiny particle-like projectiles. Something very, very odd happens. What you see below is one of the first images that were recorded of this experiment, and what you see is that each of these white dots is a single impact of an electron. However, you see that they form an interference pattern at the same time. So how is that possible? How is it possible that things that impact the screen at a definite point and therefore must be particle-like at that point when they impact the screen, they form nonetheless this interference pattern? That is one of the mysteries of quantum mechanics and what led to the whole beginnings of this business. And it's very, very easy to realize. I remember when I was in first year in physics, we did this experiment in our lab. I mean, you need some kind of setup, but it's not like rocket science. You can see this more or less with ease in your daily life, and it's something that begs the question: are these particles? Are these waves? It's the whole beginning. The other very intuitive and visible and clear particle-like phenomenon that I like to use as an example are cloud chambers. So cloud chambers are effectively some kind of compartments where you have very cold suspensions of, I think it's ammonia or alcohol and things like that, and basically some kind of critical suspension of a liquid in the air, and then when charged particles go through, they ionize and they create some bubbles, they create some trace. And so what you see below in the picture is one of the earlier cloud chambers that they were being used to observe particles. And again, this very much gives you the intuition that these things are little projectiles, right? Because on the left you have a screen with single dots where they are impacting, and on the right you have the trace that they leave, right? It's almost like you see some kind of projectile flying through, and you see the trace. This is to me, again, a very particle-like phenomenon. So these were things that were understood and they were known. And so what people did was, okay, let's build machines that basically take these particles and smash them together. So to understand what happens when you smash these particles, physicists developed an entire field of research that we now call maybe high energy physics or well, theoretical physics, maybe more generally. And we have very complicated mathematical entities, these kinds of Lagrangians, and you have all manner of formalisms. And of course, the most iconic and perhaps most recognizable are Feynman diagrams. This guy over here is Richard Feynman, who was one of the most brilliant physicists working in the United States around the middle of the 20th century, and he was responsible really for taking quantum theory and the sort of, he's the great second generation quantum mechanics guy, right? He took all the learnings from the forefathers of quantum mechanics and then brought it to the quote unquote present day. And he had this way of visualizing how particles might interact at a microscopic level. Feynman diagrams are not literally implying that particles are bouncing off each other like that, but they kind of evoke that, and they are a computation mechanism, right? So anyway, the thing is, we created this sophisticated mathematics to understand what happens when you put these particles together and you smash them, and to really smash them really, really hard, and to try and go very above and beyond what has seen before. We built these massive accelerators, right? So these are pictures from the LHC in Geneva, right? The big particle accelerator. I think it has a 27-kilometer diameter, right? So it's a 27-kilometer long tunnel that is about, I think, a kilometer deep in the ground. It's a massive thing. And effectively what happens here is that you put some charged particles, I think typically protons or some light nuclei, and they are accelerated in this tube, which is very, very, very cold. It has superconducting magnets, and so the magnets are accelerating and keeping the particles in line, and they go around the circle very, very quickly. I mean, the speeds that these things get are ridiculous. They are reaching, I think, 98% the speed of light or something like that. So it's a 27-kilometer long tunnel, and I think per second they go around several times. It's really really quite intense. And then what happens is they smash them, so they go around in different directions, and then they bend the beams and they cross, and they big explosion. And by big explosion we mean something that is microscopically very big. But you still have a bunch of sort of shards of particles that come out. A lot of new particles are created, and there's many directions that they go into. And so you use these big detectors. Here's on the left, you have these big detectors surrounding the accelerator, and you can record it. So you invent all these mathematics, come up with very sophisticated theories, quite abstract. In fact, I always say that it is almost like a cosmic joke that in the 19th century we developed mathematics like Lie groups and complex spaces and representation theory, these kinds of techniques that were developed mostly by German mathematicians and people working in very abstract problems. And then half a century later, you have people who are, observing these kinds of phenomena in cloud chambers and, hypothesizing, okay, are we observing the proton and the neutron and the electron, and what is the mass of this new particle that we are observing, that it's like a pion, it's different mass or whatever. And they could use all these mathematics that had been developed in the 19th century very effectively to model particle physics. So when you built all these machines, you were able to actually confirm that your mathematical models were good, were actually making decent predictions. And of course, maybe the most probably the highest profile case of this was the discovery of the Higgs boson. I'm sure everyone has sort of heard of the Higgs boson at some point. So I was in London at the time. I was still a student, and I remember that they canceled the lectures, and we all went to the big hall to just watch the live stream from the LHC, from the CMS experiment. And so I remember when this plots were like broadcast. It was a very, very interesting moment, because you have to bear in mind that Higgs, who by the way was based in Edinburgh, where I stayed for many years, Higgs wrote his paper in I think 1976 or sometime in the 70s. And this mechanism was assumed to be the most effective mechanism, or the most plausible explanation for mass, for the fact that particles have mass. And you have all these machines built since the 70s, so several generations of particle colliders that were built in the US, in Europe, with all this research, and slowly but surely they were recovering all the predictions that these mathematical theories, very sophisticated mathematical theories, have been done. But the Higgs boson seemed to be very, very difficult, and it was kind of the cornerstone of everything. If you didn't have that, it was a bit shaky that the whole thing would actually work. And then in 2012, this happened, and I want you to understand that this whole 27-kilometer tunnel with a tube, with the magnets. I think there was some statistic that said that the amount of cable used in all the wiring, in all the the electrical installments in the LHC is long enough to go around the sun once, right? Like the length of the cable in all that. So it is quite a massive. It's a massive endeavor. I remember around that time when I was younger, there was a documentary called The Cathedrals of Science, and this is kind of multi-billion projects that are just intended for fundamental science. Really, like this is completely useless for practical life. I mean, knowing, because at the end of the day, what you're doing is you're mashing these protons. They are coming from this direction and from this direction. They're smashing in the middle. And they have this cascade of millions of particles coming out of it. And then you run this many times, you do statistics, and then what you have in the end is something like this, where you have a background expectation, which is sort of the green line over here. You have this background expectation, and then above the expectation, there's a deviation of what if a Higgs boson existed, you would observe some kind of bump of the statistics, right? And that's it. That was enough to be considered significant and to be considered, confirmation that the Higgs boson exists. So at the end of the day, all this sophisticated mathematics just translates into a blip in a statistical graph, right? It's not like, you've discovered a new planet and you go and you can live there or anything like that. It's basically that there is some pattern in all the sparks that jump off the explosion, so to speak, of particles colliding in these accelerators that you claim the sort of the success of the theory. So anyway, so this was a very short and superficial overview of what particle physics has been like. And hopefully, from this point on, I will tell you about my research, what I work on right now, and hopefully the analogy that I make at the end will make sense. And if it doesn't, I'm here. You can ask me some questions, and maybe we can make sense of it together. So let me change entirely topic and level of complexity. I'm going to talk about what the basic objects that I work with. The objects I work with are called hypergraphs. So I'm sure everyone has heard of graphs before, or networks, I guess. They also have a name. So this is a typical network or graph, right? You have nodes, these little blue dots you have as nodes, and then you have edges. You have some kind of line or arrow connecting the different nodes. Well, a hypergraph is simply a network-like structure that represents connections that are beyond just two elements. So, for example, something like this. So you can see that there are little arrows and little lines between the nodes, between the blue dots, but there's also triangles and there's also sort of like squares and things like that. So there are connections that are implying an interaction beyond just two one-on-one connections. Okay. So that's just what hypergraph means. It has a very fancy name, but really just means that you have a network where you're representing connections of potentially more than two nodes. Okay. So the framework that I work in is called hypergraph rewriting. So hypergraph rewriting is at its core a very, very elementary process. And I will illustrate with some really nice animations in a second. But just to tell you what it is about. So rewriting is basically you specify a pattern. And for example, this pattern has, you have to check that there are 4 nodes and you find, this 4 arrows in this particular configuration and these triangles in this particular configuration. And then when you find that, the rule applies. And then what you do is, in this case in particular, you keep the 4 nodes fixed, and that's the purple ones, you keep them fixed. And then you create a new one, that's the blue one over there. And you write these new arrows. There's like now however many, that's 3 and 3. There are 6 arrows here and then 3 triangles in this one, right? And previously I had only 4 arrows and 2 triangles, right? So you somehow change the edge structure, the connection structure of these nodes, and maybe even create new nodes. So the main idea of hypergraph rewriting is that it can be used in 2 different directions, and I'll illustrate the 2 directions. One direction is what we call generative, and this is for the biologists in the audience. They are going, the shapes and kind of phenomena that I'm going to show probably will remind you a lot of biology of what people call ontogeny, right? Like the development of organisms from the first cell, right? And so this is the intuition behind this kind of hypergraph writing. So in this example, imagine that I have this little structure over here. It has just a handful of edges. It has only 4 nodes, and it has whatever, like 6, 8, maybe 8 binary edges and 4 ternary edges. And so if I apply the rule that I had, this rule is going to search for all the cases where that rule applies, and then it's going to change locally that structure, and it's going to maybe create one new node, and it's going to sort of keep getting bigger, bigger, and bigger, and eventually you are going to have some big hypergraph. So let me show you this in action, and I have a couple of applications here. I have to go out of the. Oh, I think I actually started sharing, not the screen, but give me a second. I think I need to share the screen. Yeah. So I'll share my screen, which you should be seeing the same thing now. But I'll come out of here and I'll bring this web apps that show some hypergraph rewrite processes. You're seeing this white background thing, right? Yeah. So imagine that I have a rule. It's not very visible here, but this rule is very small at the top left corner. But you can basically see that it will take some edge structure, and then it will produce, in this case, 2 edges, and it will produce 4 edges with some connectivity pattern. In this case, I have 1 node and 2 edges, and it's going to create 4 edges. So let's take one step, and you can see that this now has 4 edges. It has created also a new node, and it now has 4 edges. Now, there are several ways in which this rule can apply in this particular graph, and it will apply in several ways. So one possible way would be the next one. So now you create more edges, and then you do it again, and you do it again, you do it again, you do it again, and it keeps going. So if I just hit play, this thing keeps growing. It's choosing, in this case, I think it's just choosing at random where the rule can apply, and the thing keeps growing and growing and growing and growing. Right, so I think this goes up to 1,000 steps, and this is in some 3D embedding. So it's using a particular sort of spring-like force between the nodes to kind of simulate the tension. But that's just for visualization. There's nothing mathematically. It's just the connection. So this particular structure was born out of a very simple rule, which you can see up here. Can I zoom in here? No, I can make it any bigger, unfortunately. Yeah. But you can see that over here you have these numbers over here just mean that we have a rule that is kind of like this. This kind of rule. So it's some simple pattern that gets matched, and then you add nodes, and it keeps growing. So for example, another rule, in this case, it matches for ternary edges, and so let's just play it and see what we get. So in this one, some ternary edges are involved, and again, it's just applying the rule randomly, and it's growing the structure. So this is where I said, the biologists in the audience might start to see some familiar shapes, because the embedding is given this structure that you can see, like the sort of a kidney shape or like a bean when it's developing, and this is no accident. I mean, the reason why the shape is similar is that in biology a lot of the processes are iterative in some sense, right? Like there's a process where it keeps coming back, keeps coming back, applying some basically simple rule. Right? There may be many rules and not so simple for us to understand, but the process at the core is quite simple. So this thing was just generated with an extremely small amount of information, right? It was just an initial node with a couple of edges, and the rule is specified in a few characters. It's really, really atomic information, and then you can generate quite complicated structures. This is just another one. I just generated a few just for fun. I don't know what kind of structure you get here in the end, but I think it looks more like a ball. In the end, oh no, this looks more like some kind of rod. It has this elongated shape. It has more of like a cylinder topology in this case. All right. Anyway, so there's several things you can do, and so these are what we call the generative hypergraph rewrite systems. And so let me get back here. And we study these systems as a biologist would study some species out in the wild, right? We set up the conditions, that we set up the initial states, and we set up the rules, and we can change them, of course, and they just evolve, and we don't know exactly what they're going to do. It is very difficult to prove mathematically general results about these systems. So, for example, will the graph that you get when you run maybe 1,000,000 steps always have the same topology? For example, does it always look like a ball, or does it always have edges that are separated by degree 3 from other edges and things like that? Right? It is not very easy to be able to predict what is going to happen without actually running the system. And so that's why we study them as almost like a phenomenology of a different species. All right, so changing topics, but now we're going to look at hypergraph rewriting from the reductive point of view, and this will be clear in a second. But first, I'm going to just throw a question. So if I were there in Kyiv in person, maybe I make it more conversational and people can answer back. But I will just make you ponder for maybe 20 seconds that if you ever thought, not philosophically, by the way, I'm not asking philosophically, what is mathematics in this sort of very philosophical armchair philosophy way of like, let's go back what the Greeks meant by mathematics, what the Babylonian meant for mathematics. That's not what I'm trying to say. When you do mathematics, right? And by mathematics, I really mean anything that you're doing in science, like calculations and things like that. What is going on, right? What do you actually do? So maybe I'll take a sip of water and take 10, 15 seconds to think, what do you think is mathematics? If you were pressed to say, what are you doing when you do mathematics? So if someone wants to give me an answer because they feel brave, I would love to hear it. But otherwise, I'll just continue.
I can give you my answer
Please.
if you want. Yeah, I actually consider mathematics as an language, just a language with metaphors going to extreme in some sense. So when we talk, actually you can talk any theorem by using just expressions from language. So that I think it's just extension of language, and maybe it's already there when we just talk.
Very good definition. I very much agree. Anyone else in the cafe that want to say something?
Computations.
Okay, computation is a very good word as well. I love it. Okay, so I love that Olexii mentioned that he sees mathematics more as a language and an extension of what we normally do. And then you mentioned computation, because my answer to this is going to be basically the combination of those two things together. But before answering the question, I'm gonna try and show you something very basic. So I know that this is for grown-up scientists, but what is on the screen might be looking very formidable for someone who's learning mathematics for the first time, right? We're asked to do 1 + 2 and then add that result to 2 × 3. I mean, if your algebra is really good, maybe this is very easy, but this seems like a problem. And so when you're learning, maybe you're in kindergarten, you're very young, and you're learning these basic rules of arithmetic. You need some kind of strategy here, right? Like it's hard to say what is this going to be, right? I mean, even now you take a few seconds to really like compute, quote unquote, and know. But the point I'm trying to make is that what is the strategy here? Well, the strategy is divide and conquer, right? So let's go by step. Let's go by pieces. So if I look at the first bracket, the 1 + 2, well, that's relatively easy. That's 3. So I can just say whatever this is going to be evaluated in the end, I'm going to have a 3 in place of 1 + 2. So I first do that change. I change the 1 + 2 to a 3. Okay, but then I can independently look at 2 × 3 and say that's 6. So I will just replace 2 × 3, those 3 symbols on the paper. I'll just rewrite them as 6. And now I look back again and say, okay, but I can now do the 2 × 3 when I had the 3. So now I get this expression, 3 + 6. But it turns out that if you did it in the other order, it didn't matter. You get again 3 + 6 as the expression back in here as much more manageable, and you finally say, okay, this is 9, right? Okay, so this was totally trivial, right? Like there's nothing. I mean, people, children in the 5-year-old, 6-year-old are doing this kind of processes, but somehow, in my view of mathematics, this is at the foundation of what mathematics is about. So maybe it's not so surprising that children begin doing what mathematics is all the way, right? And when you become older, it's just a matter of doing it more and more sophisticated, more volume, many more times and more convoluted and so on. So what I want you to take away from this is that one could imagine that the system that is being processed here or computed, as someone in the audience just mentioned, is in itself having its own sort of internal life, right? So here the expression is maybe said by words or written in a piece of paper, and you write like 1 + 2 and bracket and plus and 2 and times 3 and all that, right? or you say it. But the thing is that when you make a step and you quote unquote compute, as you said, you change the symbol, right? You replace 1 plus 2, that expression, you replace it by the expression 3, right? And then similarly, 2 and the cross and 3, you replace it by the expression 6, right? So imagine that someone, someone a bit younger than someone in kindergarten looks at this and has no idea about numbers. They don't know how to count. They don't know the names for the numbers. But if you give them the rules, how to proceed, when they see a 1 and a 2 with a cross in the middle, they should put a 3. And when they, if you give them these rules just as disembodied symbolic rules of the game, they would get their correct result, right? They don't have to understand that they are adding things together, that they are taking, 1 is 1 and then 2 is 2 and then put it together is 3. Like they don't need to understand that that is the meaning of these symbols. They can absolutely correctly compute this calculation without any knowledge of the meaning. This is what people call, distinction between semantics and the syntax, right? So they can do a syntactical computation and be completely correct and have no idea of what the semantics are, right? So in my opinion, and just to maybe answer the question, because I throw it to the audience, what is mathematics? Again, I'm not going to give a grandiose answer, but I think mathematics is effectively this process distributed among mathematicians or agents, right? And that's where the linguistic component that Olexii mentioned comes in, right? I think that the foundation of mathematics is effectively doing these kinds of operations in many different settings, and the users deciding what rules they are going to apply, and therefore seeing different phenomena or different systems or different effects. So you could abstract the whole system and just say, I don't care exactly what you do, how you manipulate, 1 plus 2 or anything like that, and just say, I have some expression, that expression, I can apply rules and get 2 different expressions, and then I apply the same rules to those 2 different expressions, and then I get a single one expression, and then that one expression has only one way to go, and that gives me the final answer, right? So this is what's called a confluent rewrite system, and any of your mathematics homework from all your years in school, if it was properly written by the teacher, should have been an example of this kind of system, right? Where you might remember that there was not always a unique way of doing your homework, right? You might remember discussing with your classmates, oh, you did it this way, no, I did this way, but we got the same result, right? And maybe sometimes the teachers were really bad and they told you, no, I did that point here because you didn't do the right approach, but you said, no, but I got the correct result. And you justifiably were saying, no, I was right, I got the right result. So this is a feature of mathematics. This is a fundamental feature of mathematics that you can express different formulae with different expressions to arrive at exactly the same computation, right? Okay, so this was a very, very basic, back to kindergarten kind of explanation. But actually, this is what I do in my research. Not 1 plus 2, but this is really what I do in my research. So one of the systems that I first encountered a few years ago that actually began my whole journey into the topics that I work on these days is this particular rewrite system. So it is very abstract and very disembodied. And don't think that there's any complicated story in the background. This is really just 3 triangles that get changed into a single triangle, right? So when you find this particular pattern, you find like 3 nodes, 3 other nodes, and 3 other nodes connected in this shape that we call a fish, because it kind of looks like, like the tail and the body and the head, so we just call it the fish. When you find this particular hypergraph with this pattern, you keep all the nodes in position, right? The white dots, and you just write one big triangle between them, right? This is like saying every time you see 1 and the 2 and there's a plus in the middle, you should put a 3. The analog here is that every time you see triangle, triangle, triangle in this particular configuration, you will write a bigger triangle between the points, the extremal points, okay? So, okay, why is this interesting, or why do we care? Well, if I consider a longer quote unquote fish, so I put now 5 triangles. I mean, this is a bit small, but you can see that there's sort of 5 triangles in that expression, in that hypergraph. Then the rule applies in multiple ways. Each of these arrows here, each of these gray arrows is one rule application. So this is one fish that you can find in this larger diagram. And basically, I think it might be a bit small, but I hope you can see that there is a, 3 triangles to the left. So, 9, 8, 7, 8, 7, 6, 6, 5, 4, that forms a fish, right? Similarly, 6, 5, 4, 3, 2, 1 form a fish here on the left. And then in the middle, there's kind of a fish swimming in the opposite direction, right? That has, again, the same shape. And so you can apply the fish 3 times. What you get out of applying the fish to this 5 triangle diagram is a 3 triangle diagram that each of them look like a fish. So that seems very self-referential and somehow very symmetrical, right? And of course, once you apply the fish to each of them, you just get 1 triangle in the end. Now, why is this important? Why do mathematicians care about this? Why am I telling you about triangles and fish, if we are mathematicians? Well, the reason is that if you put names to these triangles, so now instead of just, blank triangles, I labeled each triangle with a letter. I call this A, B, C, D, and E, right? In the 3 triangles. And then every time you replace one bigger triangle for the smaller 3, you basically label that triangle with the letters. Just look maybe at the left side, is easier to see. You have the ABC here, and they all get rewritten to a single triangle, and so they are put into a bracket, ABC into a new triangle. So if you do that, and you go through the system completely, systematically, just compute, without any distinction of rules or anything like that, then you would get, again, 3 fishes, each of them with one of the smaller triangles with the letters. And then when you rewrite again, sure, you get 1 triangle in the bottom at the end, but each of these triangles have different names, right? So one is called ABC in the brackets and then the E, the other is called AB and then CDE in the bracket, and this one is called ADCBE. So B and D have been swapped somehow. So this is what mathematicians describe as algebras, right? These are 3 ways of expressing some kind of computation that you perform, and then you are invited, because really these are just the same triangle in the end. I mean, there's one single fish that goes to a single triangle. You have 3 different names for the same triangle, and what you want to say is that these names are independent, and sorry, these names are dependent because the result should be the same, which is like the analogy of you do your homework and there are several methods, and as long as you get the correct result, it should be correct, right? So you get this particular expression. This is in fact a algebra that has been discovered in the 50s in the last century, and mathematicians have studied it. And what I discovered, and this was kind of my claim to fame in some sense in this business, was that by looking at seemingly unrelated systems, right? This fish triangles, very symbolic, very kind of disembodied and abstract looking diagrams, you can get very familiar looking axioms of algebras in this way. So something to keep in mind out of this anecdote is that remember when I showed you the hypergraph rewrite systems in the first half. The first half I told you I have a small state, I apply a rule many times, and as you saw in the animations, they grow and you have these very large structures potentially. That's what we call a generative rewrite system. In this case, what we have are reductive rewrite systems, right? We begin with a more complex state, and we apply a rule that normally has some clear reductive features. Like this one, for example, takes 3 triangles into 1 triangle. So, the total number of triangles can only decrease after applications. And then you observe how the flow of the system goes after you apply in all possible ways, right? So we say that the structure of this system is causally related when you have these patterns, like that you have different names to different triangles, but then they are the same triangles, so you have some kind of equality. So I just tried to illustrate here how we are using hypergraph rewrite systems in 2 very different ways, but in both situations we have something that kind of models ontogeny and the sort of organic growth of systems by specifying a very, very minuscule rule and basically initial state, and the other by stating, I have an initial expression, this longer fish, and I'm going to apply different rules, and it's going to reduce and flow, and I'm going to have a final state, right? So those are the main ways in which we are using hypergraph rewrite systems. And so I want to make sort of my case, right? The kind of punchline of what this talk is meant to be about, and what I try to convince you that it kind of makes sense to talk about. Bear in mind that all these ideas are not new. We didn't invent any of this. I didn't invent rewriting. Stephen Wolfram didn't invent cellular automata and automated computation and all these things. None of this is new. What is new is taking this as the starting point of your research. And here's where my argument begins. So I wanted to kind of exercise with me a little when I made you think about what is mathematics, how you exercise your mathematical practice in your daily work as a scientist. You probably, I mean, nowadays you're mostly working with computers, I'm sure, but especially when you were trained and you learned and you go back to the source of the knowledge, you normally go to something that is script-like. It is written in books. It is written in documents. I mean, still, the scientific paper is the gold standard of scientific communication and scientific progress, right? So, and this is effectively sort of a flat PDF, right? It has some kind of like 2D surface with some symbols on top of it. Most of the symbols are, some verbal language, like, English or Ukrainian or whatever. The others are maybe graphs and figures and whatnot. But ultimately, if you think about it, ever since we, as a civilization, humanity has been using clay tables, blackboards, papyrus, paper, print, all these systems effectively have been computing for us in some sense, right? Like you in order to, derive a long result in mathematics, or when you're doing your homework and you're computing some long integral or something complicated, well, pen and paper is crucial, right? Pen and paper is like a computer, because unless you have perfect memory, and only some privileged humans can really do that in their heads, for the average human, and the vast majority of us, in fact, you would need pen and paper as your quote unquote computer, right? You would need to write it down, have some definitions, you would put things visually in space, and you would manipulate them, try things out, scribble, scratch it, and try it again, and so on. I wanted to think that when we invented computers about 100 years ago, let's say approximately, this path into that we find ourselves into now, where everything is digital, we have all this digital technology around us, right? It is very important to consider that most of these systems are doing a analog of what we do in paper, right? So your CPUs in your phones, in your laptops, and so on, they are basically just doing a lot of operations of things that people do with verbal language, right? When you say something like, "Oh, should I get my coat? Is it raining? Is it cold outside?" When you're doing these checks with language, and you're communicating with your friend or your partner or whatever, you say, "Hey, should we take this or that?" These kinds of logical gates, so to speak, in language, is effectively what's going on in your CPUs. And in some sense, CPUs are just at the service of us humans making use of them. And for the vast part of the last 100 years, since computers have been a thing, computers have been used to automate and iterate the computations that normally humans would do, without sort of changing fundamentally what those computations are about. Now, since the advent of this enthusiasm for automatic systems, for automata, for example, for hypergraph rewrites, like I just showed you, there has been a new science that one can do, which is to study computation in itself, right? And of course, the whole field of computer science is dedicated to that in a theoretical sense, but in an empirical sense, just like particle physics is an empirical science. You can think, okay, Imagine that we go through an apocalypse and we forget how civilization came from, but we still know how to use our computers. I don't know if any of you guys are fans of Warhammer, but this is kind of like the sort of the idea in Warhammer 40,000 is that, you know, there was a very bad war or whatever, and then all this technology that is very advanced is around, but the mentality is medieval, but the technology is futuristic, right? Imagine that something like that happened, and you still had access to all these computers. You had no idea how to build one or how to, you know, repair one, but when it's working, and you know how to use it. In that case, wouldn't it be fair to say that the computer itself is a phenomenon in the world, right? That you can define parameters and perform experiments on, right? And so when you do something like this big, maybe I can show you the actual where was it? This one. Oh yeah, I have to say. Yeah, when you take some of these systems like this big graphs and hypergraphs, where you're just like performing a lot of steps, and of course this is just for visualization. In reality, computers will do millions and millions and millions of steps at a time. You know, you could be imagining that what you do by hand, right? Which is like, okay, let's take the next expression. You know, 1 + 2 = 3, and then you have to do it by hand. You know, step by step. It's kind of similar to where physicists back in the day were observing, oh, look at this trace. This electron just left a trace in this cloud chamber, and there's this like small thing. And then when they realize that there's some kind of science that can be done around this phenomena, the particles and the you know, in the screens in the cloud chambers, they scaled it up and they built these massive machines that are very specialized in just doing particle physics stuff, the big colliders, right? And then what they do is millions and millions and millions of processes all the time and very high energies. So in some sense, when you take this kind of basic systems that, as I try to argue in the talk, are very connected to basic mathematical process, like this is what every, you know, kindergarten child is dealing with. If you scale this up to millions of times and millions of iterations, you are charting a territory that has never been charted, right? Because we never had the ability to observe computation at scale and measure it. I mean, we were only able to do this maybe in the last 50 years, let's say. And every day that passes, we have even more capacity to have even larger computers. So of course, you might have noticed that the kind of hot topic in the moment in the sort of computer world has been completely missing from my talk, which is AI, right? I didn't mention AI at all. And this is, I mean, more or less deliberate, also because I do not work with AI at all. I mean, not that I don't use some AI systems for useful stuff, but I mean, I don't research on it. But AI really tells the story. It kind of compounds the point I'm trying to make, right? We now have access to this super scaled computational power, and we are realizing that in the scale, there is novelty, right? It's not just quantitative difference, but there's a qualitative difference when you scale things up. So if you don't believe anything that I said in the last 20 minutes or so about computers and so on, if you don't believe any of that, then maybe just pay attention to what's going on in the world about AI, and then maybe you will be convinced, right? That there's something that is not just quantitative about scaling computations. And so that's why my argument here is that in the same way that we built these particle colliders in the 20th century and all this fantastical science was kind of realized, now we have the opportunity to do something very similar for computers and these very fundamental computational systems. The reason, by the way, we chose things like hypergraphs is that even though they might look a bit complicated and like the name is fancy, hypergraphs are kind of minimal, because a hypergraph is really just a bunch of dots and a bunch of lines between them. There's almost, you know, the most basic data structure you could ever imagine. And so if you want to implement something like that you understand as a computational rule, it's very easy to say, okay, all I'm going to do is like point, line into point, line. That's it. You know, like some very simple thing. And then you just study it like you just gave the genome to an organism, and that organism sort of goes out in the wild and does something, right? So that is kind of the philosophy of this sort of computational approach to the science. And so my argument is that the opportunity that we have nowadays is that you don't need a supercomputer, by the way. I mean, any random phone or laptop is powerful enough to be in the position to create very interesting science if you ask the right questions. And this is where the scientific mindset is really important, because computational power is not the point. It's about what questions you ask and what you probe and try to fish out of your system after you've run it, right? So anyway, that's sort of my point, that we are living in a very special time. I think everyone has. I mean, I certainly remember when computers were a novelty and they were not, a thing really in the world, and being able to play for half an hour some Jurassic Park game in my dad's computer was like a very special thing. And nowadays computers are just the paint in the wall. They're everywhere. It's just completely normal. I think that we have not yet matured into what computers can really bring in terms of fundamental science, which is a bit like, how long did it take for formal mathematics to develop since the invention of script, right? When humans were already writing things down and having symbols that had very clear meanings and so on. It took some time, obviously much longer than we probably take to do serious science with computers, but it took some time until mathematics, as we understand it today, began developing. And I don't mean modern mathematics in the sense of formal 19th century style, set theory style, logic style mathematics, but I mean, solving equations or solving geometry problems and so on. Those things came quite a lot later than the ability to write those things down. So my argument here is that we might be in a similar position where we just invented the technology that are computational frameworks that we have nowadays, and it might take some time to embrace them as phenomena in the world, kind of forget that we invented them and kind of study them as sort of native organisms. But anyway, that is the point. Maybe you think I'm crazy and I'm full of shit, but you can let me know. Thank you.
Thank you, Carlos.
Okay, let's proceed to the questions, maybe remarks from the from the hall.
I can tell you.
Yes.
Thank you for your presentation. Very fascinating, interesting idea about computing and related to colliders. I have a question. If taking a look on this graph, as I understand, I'm not a mathematician, but when we move through this graph, through these dots and everything, we have some kind of formal system, like we have an algorithm when we multiply, add numbers, and so on, so on. But there could be some kind of inconsistencies. Hello to Gödel. But could these inconsistencies be visualized in this graph structure? Like it breaks something or not? But do we even assume inconsistencies in these computations? Like when we start from 1 equal 2, but in more sophisticated way, we compute, and then we break something, and
Right.
Possible.
So you're if I understand your question, you're saying I think there's a first question that you're asking whether there might be errors somehow or is it errors, or when you say inconsistencies, what do you mean? Is it inconsistencies of the system itself, or?
Yeah, maybe first question, you show us an example, 1 + 3 equals something.
Yeah.
Or even, it was just a computation, but can we prove theorems with it? I mean, A equal B plus something and so on, so that we can have inconsistencies in the end, like if 1 equal 2, could it be visualized in this way, or is it seen there?
Right. So normally when people develop theorem provers, and this is something that there's been an industry of these kinds of things for some years now. Basically, since we had computers, people were thinking about theorem provers, because actually computers were invented for that in some sense. Originally, Turing and the sort of the forefathers of computing were mathematicians, and they mostly cared about this kinds of formal questions, right? So the kind of systems that I investigate are doing what those systems do. So those systems do the exact same thing. They have a state, and the state is usually ones and zeros. This sort of binary code, right? And the state just happens to be ones and zeros, and the rules happen to be normally arithmetic, right? Like the Boolean arithmetic of binary digits. So 0 + 0 is 0, 0 + 1 is 1, 1 + 1 is 0, right? So they apply those rules, and the state changed. Uh, People don't usually refer to that as rewriting, because the computers are very optimized for that kind of computation, which is much, much faster to do certain things, right? If you wanted to compute something more general with hypergraph rewriting, it would be super costly, because your hypergraph does a bunch of stuff that you don't care about, and you have to kind of put it in a box and then say, I don't care about all that computation. I just wasted 200 years of compute power into that or whatever. So my research is about the systems that are operating in things like theorem provers. And my particular research, my particular approach to the questions in algebra, so that these kinds of questions where you have some kind of symbolic rewrite system like this fish, and then you get something like a theorem, right? This is an equation, right? Something that you say you proved, right? In some sense. These are more like what I was saying, more like the blackboards of the future in some sense. This is emulating how mathematicians might communicate about mathematics on a blackboard. So in some sense, the blackboard itself doesn't know what is true and what is false, right? It doesn't have a sense of truth. It doesn't have a sense of consistent or inconsistent. What it does is it allows you to basically imagine that your pencil or your pen when you're writing knows algebra itself. So in some sense, when you're going to make a mistake, it basically doesn't let you write it. It's like stopping you. So this is the idea, right? That the system knows exactly how to operate, and by definition, it will only operate in this way. But unless you have some previously known result about where the system will go, you have no idea what the system is going to do. So you have to actually run it, which is to say, like in science, you need to make an experiment to get the data and then infer something. People didn't know whether the Higgs boson was going to show up until they smashed these protons at super high energies, and they got this blip in the graph, right? This is the kind of analogy that as opposed to something like theorem proving, where you have a well-defined sense of truth, where you have an expression, that expression can be consistent or inconsistent, right? If you get to something like 2 = 1, that's clearly inconsistent, so you know that something was wrong along the way. That is not what we do here. We are more in the realm of science than in the realm of mathematics in this sense, right? And that's why it's kind of, some people call it experimental mathematics. I don't know if anyone has heard the term experimental mathematics. It's not because you are experimenting, like trying things out. That's not what it means. It means, it could also be called empirical mathematics. So you're studying systems that represent mathematics, like this, right? Like these expressions that represent mathematics, or this certainly represents mathematics, arithmetic, but you maybe abstract it a little bit and you use these triangles instead. And maybe if you label, you have these expressions. And what you do is you let the systems evolve, with their own life, and then see what happens. So it is purely mathematical and abstract in the sense that the content of the system itself is like formulas on a blackboard. But the behavior of the system is very much like a living being, because you just say, here's your rules, which is basically to say, this is your genome and basic metabolism, and then off it goes. You just turn on the computer, you hit play, and it keeps going, like the animations that I showed, just keeps doing its thing. And then the question is, what do you ask of these things? Because obviously, since you run it on a computer, you basically have perfect information of everything. Right, you can look at all the steps. It's a bit like people running AI systems. They have perfect information of what the AI system is doing. That doesn't mean we understand how they work, right? We don't really understand how LLMs exactly do what they are doing. I mean, we build them, and we still don't really understand them. So this is, that's why I said, if you don't believe anything I just said, just pay attention to kind of what AI is doing, and it's kind of a larger scale example of what I'm trying to say here. So maybe that's a good summary. Just to take your question as kind of a prime to or a prompt for me to answer is that our systems are mathematical in nature, but are somehow natural in behavior, right? They have a life of their own, and we just want to observe and ask. So it's similar to that, observing things for the first time. Like first time you see a species of birds, it's like, okay, where's the genealogy of that? How are they related to something else? So this is what we are doing. We are kind of charting territories that are unknown, and to create those territories is basically we have to generate them in a computer, right? So yeah, it's interesting. I mean, it kind of prompts some philosophical questions about what is real and all that stuff, but maybe we shouldn't get into that. Yes, that's another question.
Okay. My question may be considered as a natural extension of the previous one by my colleagues. But okay, I'm not expert in both in graph theory and in Lean programming language, but is it possible to combine Lean and these generalized graphs somehow and to generate or to derive mathematical derivations, mathematical theorem derivations, or something like this?
I didn't hear probably. Did you hear Lean?
Yeah, Lean programming.
The system, yeah. So I would answer something similar. Because Lean is, I actually know the main developer of Lean was my teacher back in London when before Lean existed. So I know him quite well, and we talked about it quite a lot. So Lean is actually it's very focused on doing mathematics, right? And mathematics has a very strong sense of truth. I mean, that's kind of the whole business, right? Like something is true or false, and you can prove by contradiction, and like all the so truth is a very fundamental notion there. We just have no sense of truth in these systems. So answering your question directly, yes, you can put graph data into Lean and use the Lean system to make derivations of our systems. Now, the other way around is going to be quite costly, because the other way around means that we would have to somehow come up with a way to encode truth in a particular rewrite system, which might be very complicated. So, for example, have you heard about SK combinators? Have you never? So there's these are very simple symbolic systems that have only two rules and only two symbols, S and K. That's why it's called SK combinators. So you have only two letters, S and K. It's a bit like binary, but even simpler, because it only has two rules. And when you find an S and an R, sorry, an S and a K and an S, they do something. It's very simple, right? So two very simple rules. It is possible to generate all of arithmetic with this system. So in some sense, you have the entirety of mathematics implemented in this system, which just has literally two symbols and two rules. Now, is that useful? Probably not, right? No one is really using SK combinators to prove everything, right? But people who worked in formal systems, in formal languages, in formal verification, they're interested in these kinds of questions. So Lean is very much in that business of doing formal verification. Our systems, however, as I say, they are trying to encounter mathematics out in the wild, so to speak. Lean is like a well-kept garden where everything is mathematical by construction. It takes a lot of work, and in Lean they work by fields. You get an update, they say, oh, they just formalized whatever undergraduate ring theory or undergraduate commutative algebra or whatever. And you have this entire fields of mathematics formalized in Lean. So it's like a very well-kept garden where everything looks mathematical. But if you step out of the garden, there's nothing, because Lean only is really for that. Our science is more about the entire field of computation. So mathematics, as we know it, is some area that we are trying to fish out. In fact, this is exactly what the point of this diagram is on the screen, that by using this particular pattern of triangles look like a fish, we were able to fish out this particular algebra. And this algebra has a name, has been studied. And by the way, much simpler diagrams give you algebras that are much more familiar. So for example, if you put 3 arrows in a row, that pattern gives you associative algebras. If you put like a dot and an arrow, that gives you what people call groups and group actions and things like that. So very, very simple diagrams will give you known mathematical theories. But the point is that those simple diagrams are just one or two in a vast field of possibilities of combinatorics, right? And so our research is about, can we develop a science to identify the algebras out in the wild? It's a bit like, being a zoologist going out in the wild and finding animals and saying, okay, what is the taxonomy that I should be using? Because you see suddenly like a yellow bird, and then whatever, like a badger mole, and then you see an eagle, and then you see a monkey or something, and it's like, okay, I need some kind of system to, and then you develop basic idea of genetics and hereditary processes and all that stuff, and to explain the status quo. So we are kind of in that business. That's why I say the content of our research is very mathematical, but the methodology is scientific. It's empirical in nature. So it's kind of odd because when you talk to audiences, you lose all the mathematicians or most of the mathematicians because they realize that you're not doing mathematics as it's known, and you lose most of the scientists because you're only caring about mathematics in the end. So it's a bit unfortunate, but I hope that gives you some idea of an answer. Yeah.
But just a funny note, you have said about you exploit scientific methods against mathematical objects, and we always joke it when I was a student that math is not a science.
It's not a science, exactly.
Yeah, it's not science in the natural science terms.
Correct.
Yeah.
Yeah, I would agree. I would agree with that. I would say mathematics is not a natural science, and this is an attempt at doing natural science that can say something about mathematics. So that's why maybe it's a bit controversial, a bit weird. People don't exactly understand it. But yeah, but it's fun. I can say that.
Back to your question, what is a math? You also can say that the math, we don't know what is the math exactly, but we can say that it is a very useful language to describe the world.
Yes.
But we don't know what is it exactly.
By the way, actually, recent artificial intelligence and LLM, which are pure math and data, maybe create math as a science, as a natural science, because now we have an object to actually explore and try to understand.
Yes. I mean, when you think about when I use the example of AI to say, if you don't believe anything I'm saying, just look at AI. We are building these systems, and they are like alien races, right? I mean, it's like we suddenly encounter. You can talk to them. You can ask mathematics question. They answer correctly many times. Most of the time, I would say, for the simpler stuff. And they also lie to you a lot, so it's interesting. but effectively, we are creating an alien race. Like I never expected that our contact with a different intelligence was going to be artificial, right? Like you always thought, okay, maybe there's like some spaceships are coming, but actually, I think we are in our lifetimes. If everything keeps in this trajectory, we're going to probably witness proper human-like intelligence and probably super intelligence in some dimensions in our lifetimes, right? So it means that you might be able to say, okay, think about this mathematical problem, get back to me. And they spew some ideas, and if they are mathematically correct, this is mathematics. In any other field, there's might be some other considerations, but in mathematics, it's like, okay, this is a hardcore result that this system just managed to suggest, and then you verify it and it's correct, right? So it's really quite exciting, and in some sense, I am very, I wouldn't say scared, but it's such a uncertain prospect, and I actually worked a little bit in not AI but in machine learning infrastructures. So the mathematics, as you might imagine, the mathematics of networks and hypergraph computing actually are quite useful for some of the architectures that AIs use. So I actually have a collaboration with a couple guys in the US working on this, on sort of the machine learning foundations of machine learning and things like that. And these people are at the top of their game. They are really like at the forefront of these systems. They have no idea how they work. No one really knows how they work. You know how to build them, like, and this is similar to a particle collider. You knew how to put the particles together, but once you turn it on, you smash the stuff and you start measuring what comes out. That's crazy, right? I mean, for the physicists in the room, you have to bear in mind, I don't know the chronology exactly in my head, but I believe that the first, I think the neutron was discovered in the 30s or something like that.
Yes, exactly.
1930s, yeah. So you have to bear in mind that you went from a view that atoms and maybe protons were kind of like everything. It's light, electrons, and protons, and that's everything in the universe. And then just by doing something funny, which is like put these things in like a big accelerator thing and smash them together, then suddenly you got this like zoology of particles, like the pions and like all the different mesons and like all the crazy stuff and all the other leptons and different generations. And I mean, that's not even counting the quarks that you might think that are underneath, but even the things that you would observe like in detectors, it's just like crazy, like all this diversity stuff. And suddenly it's like, what did we just do? We just like press the button, like a bit more temperature in the system, and suddenly it explodes. I feel like we are doing something similar with computers, and AI might be one of these systems. I hope that some of these hypergraph systems have something similar in them, that you just turn them on, you measure the right thing, and suddenly you are discovering new mathematics. This is, by the way, this is kind of one of my punchlines, that we're hoping to discover new mathematics. I thought I had discovered mathematics in this fish example, but it turns out that someone wrote a paper in the 50s that already defined the algebra. So I cannot claim that I discovered it with hypergraphs, right? But anyway, it is the sort of vibe of the moment, that these computers are not only extremely useful for our kind of technological lives, but scientifically, we have just created a new field for us to go and explore, and it's quite distinct because we have perfect information of what we are doing, right? Like, it's just a matter of how to dissect it, how to what statistics to run, what mathematical theories to do on them. And of course, it makes sense that people are developing psychology of AIs, right? Like, because it is actually sometimes better to understand psychologically an agent than computationally. Because if you try to understand what the min-maxing and all the the intermediate layer processes, that's hopeless. There's too much information there. But if you have an understanding that they are trying to lie to you and they're deceiving you, and you're playing some kind of game theoretic approach to an agent, that might be much better, right? And so, yeah, very interesting stuff. I would love to actually spend the time, but hopefully in a few months I will be in Kiev. So hopefully I'll be able to join you guys.
No question. It's the first time today I hear, just recently heard about psychology of AI, but does it have any sense to create a psychology of a system with development cycle lengths like months, because of AI agents replaced by new versions every several weeks, every several months? Does it have any sense? Because
no, that's very interesting.
Because we are studying system which will be out of date within several years.
That's true. That's totally true. I mean, and that's part of the problem, that anything that you can say with more or less confident about one model, when it's updated and trained differently, and it's gone, right? Which is kind of what happens with people, right? If you try to apply the societal expectations of the world today to someone who lived in the 17th century, well, it's not going to work that well, right? Or or different languages, like if you don't speak the right language with them, like they're not going to understand. So someone who speaks a foreign language seems totally dumb to you. It's like, what are these people saying? It's just gibberish. You don't get anything, right? So it's certainly an interesting point. And I will mention something now that some biologists are in the audience. If you are interested in this direction of ideas, I mean, you mentioned the psychology of a system. So there's a scientist in the US called Michael Levin. I don't know if some of you have heard of him. Michael Levin is a developmental biologist. He worked in sort of ontogeny and these kinds of things. So I really encourage you to go and check his work. He has some ideas about how biology and intelligence and many other processes in the universe are kind of one and the same phenomenon that he would call something like extended cognition or the cognitive phenomena, right? And I very much agree with this perspective. And of course, AI being just another example, right? So these are cases where you have completely different substrates. So you have an anthill, a colony of bees or ants. You have a human brain. You have a supercomputer. Google running Gemini or whatever, ChatGPT. You have a swarm of birds, a flock of birds. These kinds of things, they operate almost indistinguishably, right? Like you can assign a sort of psychology to them, where there's an agent, there's a self-preservation, there's a teleology, right, of setting objectives and attaining objectives. There is a optimization of and self-preservation, as I said, and then game theoretic concepts apply to them. And suddenly there's this kind of, it's almost like a phase transition where you go, where does your system obey like differential equations, and when does your system obey game theoretic concepts and psychology and things like that? It doesn't, I mean, typically this is almost pseudoscientific to say, oh yeah, you have to apply psychology to, no, that's not, but we are in a world where really they have papers where they're saying this system, and this is really just like a bunch of gas suspension particles in some like physical system. They say this system is really governed by these differential equations and some diffusion equations or whatever. And then they change some parameters, they introduce something else, and then the system starts to behave with memory, for example, that the system actually stores its own history to a degree where differential equations are no longer useful, and it's more useful to employ like agent-like modeling for that system, right? So if one is very open-minded and really honest about the science, and it's not sort of dogmatic to think that differential equations are the hard science and everything else is sort of like mumbo jumbo, this is very serious. And the question is, okay, how do we make this less solid looking science, like psychology like arguments, into hardcore measurable science? And that's kind of the process, right? And part of the way is to do emulations and simulations like these systems that are exact, computable, but unpredictable until you actually run them, right? That's part of the business. So yeah, super fascinating stuff. Not the stuff I work on, unfortunately, but super fascinating stuff.
Is it viable to use this system, this hypergraph approach to discover something new, to create new theorems? It just reminds me of one sci-fi book. They had like a mine of knowledge. And it's like, I imagine it like you dig deeper into the ground, and each root, each trace is something as a humanity discovered. It's from Greg Egan Diaspora, if someone wonder. One character answered, why can't we just dig everywhere and find the real? It's just impossible because it's too much computation, too much work.
Right.
So the question, can we use this hypergraph system to predict or discover something new?
I love your question, because this is exactly why I got into this in the first place. I mean, my personal motivation was to discover new mathematics. So that's why I invented these things. I mean, I invented these kinds of diagrams. It's not that I invented, any of the foundation of this stuff, but the way I do this and the way I search for algebras in these hypergraphs, like the fish, is sort of my idea. And the whole point, and I won't go into all that direction because that's more for mathematicians. In fact, the talk I gave at the University of Lviv was more about the mathematics that motivated me originally. But the motivation was really, can I discover mathematics that we have not discovered yet? And there's a very funny story that, when I began studying this 3 years ago, this is obviously not a formal argument or a scientific argument, but it's more like a sociological argument. So 3 years ago, when I started investigating this actively and publicly, so I put some papers out, I gave some talks, and people started to like see this in conferences and so on. Since that time until the present, I've gotten around 3 or 4 emails, 3, 4, 5 emails from complete strangers, people I never met before, that they were just emailing me saying, hey, I just found your paper or just saw your talk online or something. And they tell me, 20 years ago, I had a similar idea. I looked into this, but I never got anything. So it was very interesting that independently, four or five people approached me saying, "Hey, I found something very similar, but I never quite figured it out." And this is unfortunately the frustration, right? Because these algebras are a bit too big to write down, so most people just won't write them down, and therefore, if you don't write something down, you're not going to think about it a lot, and because there's almost no tools to reason through them. And then these systems might be able to tell us things about those algebras, right? These systems might be able to tell us, oh, you might not be able to say to prove a theorem, so to speak, but they might be able to say this algebra can compute this kind of operation, and that cannot be computed efficiently with these other algebras, right? Things like that. So yeah, the intuition that you have is completely correct. Like the way you imagine this is that there's a kind of a Platonic universe of all possible rules, right? If you ask Stephen Wolfram, he would say something like the Ruliad or something, some fancy name that he invented. But it's just a very simple idea of you think of all possible states and all possible rules that apply to those states, right? In fact, if you think of all possible states, is already all the possible rules, because all the rules are all the ways that you turn one state into another in some minimal way. So, so if you think of all that, you have to imagine that, all of mathematics as we know it is there, right? It's somewhere in there. And of course, there's a lot more than we don't know that is also there. But there are two interesting questions, and maybe I'll say this as a kind of closing remark. Unless there's some more questions, I'm happy to answer. But for my side, that would be me done. There's two interesting questions there. First, are there mathematics that we haven't discovered that are very useful for humans and very usable for humans that are out there to be discovered? That's one question. Second question is, it is a fact that in this vast universe of possible computations, there are many redundancies, right? You can do many things. You can do the same thing in many, many different ways. In fact, you can show that you can do any one thing in infinitely many different ways that are equivalent somehow. So then the question is there a notion of prime structure, right? So you know that numbers are infinite, but you only need, for any given number, you only need a finite number of primes to express it as a product, right? So is there such a thing as a prime rule, right? Where any other rule, there are infinitely many, can be built out of the prime rules. And then the follow-up question is, if you identified a bunch of prime rules, can you get all of the known mathematics and more that we don't know with the prime rules themselves, right? So these questions are highly non-trivial. And the problem is that you don't even know when you're answering them, because since you are discovering new mathematics that don't have applications, because you are doing exploration for the sake of exploration, it's hard to tell that you've made any progress, because you might find a system and you say, yeah, this is new mathematics, but until maybe 50 years in the future, when someone says, oh yeah, my system of whatever, like, really needed this thing and we used it, and then now it's part of the culture of mathematics, right? It's it's very interesting.
It's so cool. You talk like a Platonist, this idea, the math and everything, but at the same time you develop a quite empirical approach to this. So,
yes. It's a very, I agree. It's a very interesting rebalancing of we are totally operating in this Platonic world, but it is very empirical. I'll tell you an anecdote. When I was early in the research project, I had a question about a hypergraph. I was looking for one hypergraph. By one, I mean I needed a hypergraph that had some specifications. It had to have 9. It was a hypergraph made of triangles, so a bit similar to this kind of thing that I had earlier in the talk, like kind of similar looking thing to this. But it was actually quite small. It just needed 9 triangles in however many nodes. So what I did was, okay, let's draw. I started drawing, trying to imagine. It's like trying to solve an equation, right? Some kind of formula. I was like drawing different hypergraphs. Like maybe I started like even building models with like triangles, like with physical triangles just putting together, like trying to imagine them in space. And then, I couldn't figure it out. Okay, I desist. So what I did next was I downloaded a formal proof verificator, one of these formal proof assistants, and I told it, okay, I want a hypergraph with these characteristics, and then what the program does is it generates all the isomorphic hypergraphs up to that size, right? So it generated everything up to that number of triangles. And so it turns out that they were like, I don't know, 1.5 million hypergraphs of that characteristic. And it was so interesting because, the computer ran for 2 days, and just my laptop, it ran for 2 days, and, it produced all these hypergraphs. And it was interesting because in some sense, I was very happy when I saw it completed, when the computation was done, because I thought it was going to crash or it was going to be too big. But no, it was okay, finite and manageable for the laptop. And it's like, okay, great. I have my solution, because I knew that the hypergraph was there, and therefore I had solved the problem, right? Like I generated all the and then I realized, I sat down at the desk and thinking, so the hypergraph is in the memory of my computer right now, but how do I get it out? I have another 1.5 million hypergraphs in my memory. How do I actually find it? And so that's what got me into this kind of styles of ideas, where I'm trying to look for patterns, and look for rules that apply locally and so on, like to do some kind of scientific measurement, not to just like literally be lucky and put the hand in the bag and take one out of 1.5 million and be lucky and get the one you want, right? So it was a moment of reflection of, okay, the question is Platonic in nature, because I'm asking about the existence of a single hypergraph that I knew existed, but the answer is completely empirical, because it's actually in the bits, in the ones and zeros of my hard drive where this was stored. It was there somewhere, right? It was an empirical fact that it was stored there, but it was a scientific problem for me to try and get it out of the hard drive and for me to understand it, right? So it's I love your remark that this is living as in a bridge between Platonism on the one hand, but on the other hand is extreme empiricism, because you have to actually make the machine do the thing, right? So yeah, it's really cool. I have to say that, just as maybe more of a personal comment, I never quite liked computers. I'm not the programmer type. I'm not a programmer. Like I don't spend a lot of time coding. When I code where I need to, but I'm not fond of programming. I don't find a lot of enjoyment in it. I prefer to play the piano or play some video games than to code. Some people like to code. I don't love coding. I'm not a programmer type. I never use computers other than for arts, like for video games or design and these kinds of things. But since I got into this areas of mathematics, of like, with the diagrams and the hypergraphs and so on, I realized, okay, computers are really like the pen and paper of the next century. So I should get up to speed and really take it seriously in that sense. So yeah, very good questions. Thanks for those questions. Those really very well directed.
Thank you.
Any other questions?
Oh, sorry. There were a few comments about game theory, so I was a bit,
Yes.
yeah. But yeah, no, I think we should, if no any other questions or remarks, then we can thank you, Carlos. What is the proposal?
I think we can thank to Carlos. Yes.
And we will expect you in Kiev in person this
Yes.
year, someday.
Yes,
Yeah,
hopefully
that
sometime in
would be
August.
great to meet offline. Yes.
Yes. I look forward to that. Hopefully in I don't know, 4 or 5 months I'll be there. So
Let's try to connect some dots. Yeah.
absolutely. All right, everyone. Really appreciate it. Look forward to meeting you soon.
Bye.
Bye.
Thank you. Bye.
Bye.
Здорово.